Hello everyone, this is Professor Roman. Let us continue the ring theory lectures. We are ready now to discuss Chapter 7, Chain Conditions. Finiteness conditions are quite common in algebra. For example, in linear algebra, having a finite dimension is a type of finite condition on vector spaces. Also, in group theory, having finite exponent is a type of finite condition on groups. It's not as strong as the group being actually finite, but it's still a finite condition. So is the condition of being periodic. In ring theory, the chain conditions on ideals provide a kind of finiteness condition. Here is the definition. Let R be a ring and let F be a non-empty family of ideals of R. The family F satisfies the descending chain condition, often abbreviated DCC, if any descending sequence of ideals in the family must eventually become constant. And so that means that there's an index n for which I sub n plus k equals I sub n for all k bigger than or equal to 0. In other words, from I sub n on, all of the ideals are the same. I said descending sequence, but I wrote descending chain. And let me explain. This is, of course, a sequence. Chains, as you probably know, can be more general than sequences. They can be uncountable. So this is a descending sequence, but common language seems to use descending chain more often in this context, so I'll stick with that. Dually, a family F satisfies the ascending chain condition, abbreviated ACC, if any ascending chain of ideals of this form must eventually become constant. Now, our main interest in these two concepts comes when I is a given ideal of the ring R, and F is the family F sub I of all ideals of R that are contained in I. Now, of course, this also includes the case where I is all of R, and so the family is the family of all ideals of R. That's the most common case. So, definition, let R be a ring and let I be an ideal of R. Let F sub I be the family of all ideals of R that are contained in I. And again, I'll say, this also includes the case of all ideals for the ring R. The family F sub I has the DCC. If it has the DCC, we say that I is Artinian, and that's named after a famous German algebraist named Emil Artin. If the family has the ascending chain condition, we say that I is Noetherian, and that's named after an equally famous German algebraist, Emmy Noether. A very interesting lady. You might want to Google her name, and you'll see some interesting things. Okay, here are some examples. The ring Z of integers is Noetherian but not Artinian. By the way, I realize that it's going to take a little time probably to make the connection. Artinian, which chain condition is that again? Is it ascending or descending? Same thing with Noetherian. It takes a little while to get comfortable with these names, so don't be discouraged if that happens to you. It took me a little while when I was a student to sort that out. Artinian is the descending chain condition. Noetherian is the ascending chain condition. So, the ring of integers is Noetherian, It has the ACC, but it's not Artinian, does not have the DCC. To see that Z has the ACC, if you had a strictly increasing sequence of ideals generated by K sub I, and we can take these to be positive, then the chain of generators, the set of generators, forms a strictly decreasing infinite sequence of positive integers. And the order now is just the usual order, right? So K sub 2 is strictly less than K sub 1, K sub 3 is strictly less than K sub 2, and so on. And that sequence has to terminate. It has to eventually become constant. I should have said it that way. And so the chain of ideals has to become constant. And therefore, the integers has the ascending chain condition. But here is a strictly decreasing descending chain of ideals. So the integers is not Artinian. I'm going to leave for you to check that the ring of polynomials over a field is Noetherian but not Artinian. So it has the ACC but not the DCC. Just the reverse of the example we just gave. The ring of not the reverse. It's the same. It's Noetherian but not Artinian. Okay. Same as the integers. The ring of polynomials in infinitely many variables has neither chain condition. And I'll also leave it to you to show that any finite ring is both Artinian and Noetherian, has both chain conditions. Any field has both chain conditions. So the examples we've just been through show that there are rings that are neither Artinian nor Noetherian, neither chain condition, both chain conditions, ascending chain condition but not descending chain condition, Noetherian but not Artinian. What I didn't give you is an example of a ring that is Artinian but not Noetherian. So it has the DCC but not the ACC. And the reason is because I cannot. The Akazuki-Hopkins-Levitsky theorem, try saying that fast 5 times. It says that the descending chain condition implies the ascending chain condition. DCC implies ACC. Artinian rings are Noetherian. And this theorem was proved for general rings by Charles Hopkins and Jacob Levitsky in separate papers in 1939. But Akazuki had proved the result for commutative rings a few years earlier. And in fact, I will prove for you the commutative case at the end of this chapter. I believe that neither, I had read anyway, may or may not be true, that neither Emil Artin nor Emmy Noether was aware of this fact, and this connection. They may have, in fact, thought the two chain conditions were independent, which is quite interesting, I think. Kind of gives hope for the rest of us, because they were true mathematical geniuses, both of them. There are some useful characterizations of, that's plural here, of Artinian and Noetherian rings. They're simple characterizations, but very useful. And just to remind you, an ideal I of R is finitely generated if it has a finite generating set. And incidentally, we're going to be using some of the results from Chapter 2 here rather heavily, and on co-prime ideals, maximal ideals. So if you're feeling a little shaky on that, since it's been a while since we've covered Chapter 2, and we had kind of a respite from that material in the chapter on polynomials, you might want to go back and take a look at some of that before going on with this chapter. That's up to you, of course. So here's the characterizations. For a ring R, the following are equivalent. R is Artinian. That's the DCC. R has the minimal condition on ideals, and that means that every non-empty collection of ideals of R has a minimal element. The following are equivalent. R is Noetherian, and R has the maximal condition on ideals, which means that every non-empty collection of ideals of R has a maximal element. And there's a third condition that we don't have in the Artinian case, and that is that every ideal of R is finitely generated. As to proof for this first part, suppose first that R is Artinian and that M is a non-empty collection of ideals of R. If an ideal I1 in M is minimal, of course we're done. If it's not minimal, then there's an ideal I2 in M strictly contained in I1. If I2 is minimal, we're done. If not, then there's an I3 strictly contained in I2. And we're beginning to form a strictly descending chain. This has to stop. And when it does stop, we have found a minimal ideal. For the converse, suppose R satisfies the minimal condition on ideals, and that we have a descending sequence of ideals. Then the family of ideals in this sequence has a minimal member, say I sub n, and that implies that from I sub n on, all of the ideals are the same. As to part 2, the equivalence of being, let me go back, the equivalence of being Noetherian and having the maximal condition on ideals, the proof of that is very similar to the proof I just gave, so I'll let you deal with that. We have to deal with the maximal, with the ideals being finitely generated. So, suppose R is Noetherian and I is an ideal of R. If I was not finitely generated, we could take an element A1 in I. That doesn't generate all of I. So there's another element A2 in I, for which this holds. This does not generate, A1, A2 does not generate all of I, so there's a third element, and we can construct an infinite, strictly increasing sequence in this manner if I is not finitely generated. Well, that's a contradiction to the ascending chain condition, and so the ideal I must be finitely generated. This is a very similar argument to the one I just gave. Conversely, if every ideal of I is finitely generated and we have a sequence such as this, an ascending chain of ideals, then their union is an ideal. Therefore, it's finitely generated by, say, generating set G. G is contained in one of these ideals. And from that point on, all the ideals are the same. So we have the ascending chain condition. This is a very common argument, this proof, and it's definitely worth studying until it makes perfectly good sense to you and you can reproduce it yourself. If a ring R is Noetherian, so then is every ideal of R. We're just restricting the family of ideals to which the ascending chain condition applies. If it applies to the bigger family, it applies to the smaller family. Same thing's true for Artinian. In addition, if R is Noetherian and I is an ideal of R, then the quotient is also Noetherian. That follows from the correspondence theorem, and I'll let you think on that. It happens the converse also holds for both Noetherian and Artinian. Let R be a ring, let I be an ideal of R, then R is Noetherian if and only if both I and R mod I are Noetherian. And similarly for Artinian. And here's the proof, say in the Artinian case, and let you do the proof for the Noetherian case. So assume first that R is Artinian, has the DCC. Then, as I said, I also has the DCC, and the correspondence theorem implies that R mod I will have the DCC because every ideal of R mod I has this form, J mod I, where J is an ideal of R containing I. So a descending sequence of ideals in R mod I has this form, and since the numerators form a descending chain of ideals, it must become constant. And therefore, so must this chain. Because the numerator, the chain of numerators eventually becomes constant, so does the chain of quotients. For the converse, if we have a descending sequence of ideals, and we want to show that this must become constant at some point, we get to assume that I and R mod I have the ACC. Have the DCC. Okay. So this sequence, we intersect this sequence with I, we get a descending sequence of ideals contained in I. And so this sequence must eventually become constant. Notice that if any of the ideals, I sub n, is contained in I, then of course all the ones following will be contained in I. And so this intersection will be equal, say I sub n plus k intersect I will be I sub n plus k. So these two sequences have the same tail starting at index n. And so if this sequence eventually becomes constant, so will that, and we're finished. So we can assume that none of the ideals in this chain are contained in I. Now we can look at this sequence of quotients. And because of this assumption, this chain is a decreasing sequence of non-zero ideals. Okay. Therefore, this sequence must eventually become constant because they're ideals of R mod I. They're non-zero. And that implies that the chain of numerators has to become constant. So there is an index n for which in intersect I is the same as in plus k intersect I. So from the index n on, the intersections are the same. Also the sums are the same. Those are the numerators. Now, of course, in contains in plus k, by assumption. For the reverse inclusion, if x is in in, then x it also belongs to in plus k plus I. So it has this form, little in plus k plus little I, where little in plus k belongs to the ideal in plus k, and little I belongs to the ideal I. So little I is x minus in plus k, which is in in. So I belongs not only to in, but to I, and that belongs to any ideal farther along in the constant sequence. And that's contained in in plus k. So x belongs to in plus k. And these two are equal. So the sequence of I sub k's becomes constant. And R is Artinian. Okay. You may have to read this a couple times to see what's going on. Maybe you can find a way to explain it more clearly. There's nothing wrong with that, but maybe it's not telling you what's going on really very clearly. Now let's take a look at Therian rings and then Artinian rings separately. There are lots of Therian rings. And I'm going to leave proof of this theorem to you. Any principal ideal domain is Noetherian, has the ascending chain condition. One of the main results concerning Noetherian rings is the famous Hilbert basis theorem, which says that the ascending chain condition is inherited by polynomial rings. So if a ring R is Noetherian, so is the polynomial ring R square bracket x. The proof of this is a little bit taxing. It's not terribly deep, but it's a little hard to explain really clearly. So, in fact, I've written and rewritten this proof several times. I hope this is going to be clear. And it goes as follows. First of all, to avoid some really minor complications, but annoying ones, we'll assume that R is commutative. To prove that R square bracket x is Noetherian, we will show that every non-zero ideal I in R square bracket x is finitely generated. For some notation, if p of x is a polynomial over R, we'll denote the leading coefficient of p of x by LC of p. And if S is any set of polynomials in I, we'll denote the set of leading coefficients of the polynomials in S together with 0, and that's important, by LC sub 0, LC naught of S. Okay. Now, our main tool, of course, in this proof is the fact that every ideal of R is finitely generated. That's our only tool, in a way. One place to find ideals of R is to extract leading coefficients from some or all of the polynomials in I, and then we have to toss in 0. In particular, the set LC naught of I is an ideal of R. So that's the set of all leading coefficients of all the polynomials in I. Also, this set, if I sub k denotes the set of all polynomials in I that have degree k, LC naught of ik is an ideal of R. I debated whether just to let you prove that or not, but I went ahead and gave you a proof here, and I'm going to skip over this because it's something you should try to do yourself before reading what I've written here. So, LC naught of S. S is either I or I sub k. So LC naught of S is an ideal, therefore it's finitely generated. So LC naught of ik, for given k, generated by a finite set of elements, it's this ideal. Also, LC naught of I, generated by a finite number of elements, this ideal. Now remember, these are leading coefficients, so they come from polynomials belonging either to I sub k or to I. So there are finite sets of polynomials, p sub k, this is the finite set contained in I sub k, or this finite set contained in I, for which the leading coefficient of one of these polynomials, p ki, is aki, one of the generators of these previous ideals here. And the leading coefficient of p sub I is a sub I. So we've got two sets, well, we've got infinitely many sets of generators of leading coefficient ideals. We switch over to the polynomials from where those leading coefficients came. Also, now all the polynomials here in this family have degree k, because they belong to I sub k. These polynomials, however, we don't know what the degrees are. However, we can always multiply any of these polynomials by a power of x to bring all the polynomials to the same degree without changing any leading coefficients. So we'll assume that these all have the same degree, call it d. So now the polynomials in any of these families, p sub k or in p, have the same degree. Consider this union. We take all of these for index k less than d, and then take this one, and I'll call those polynomials q1 through qm. It's a finite set. This set has a special property. It can produce a polynomial of this form, so it's a polynomial combination of q1 through qm. Therefore, it belongs to the ideal generated by this union. It can produce a polynomial of this form with any desired degree k and any leading coefficient a belonging to a polynomial in I sub k. So degree of f is k, leading coefficient of f is a. You pick the degree, you pick the element you want to be leading coefficient of a polynomial of that degree, and you can find such a polynomial of this form. And to see this, if k is less than d, then a, of course, belongs to LC of ik by assumption. So there are elements R1 through Rn and R for which A has this form. That's because that's what the ideal LC naught of IK looks like. This is the leading coefficient of this polynomial combination. It's actually a linear combination in this case. So this polynomial has degree k and leading coefficient a. On the other hand, if k is bigger than or equal to d, then a belongs to whatever leading coefficient ideal we've chosen, but that's the leading coefficient of a polynomial in I, so we have a can be expressed as this linear combination, which is the leading coefficient of this polynomial. Notice the x to the k minus d. I need this to raise the degree to degree d. So this polynomial has, degree k and leading coefficient a. So this set U has this special property of being able to reproduce polynomials, of being able to produce a polynomial of a desired degree with a desired leading coefficient. And that property, in fact, implies that I is generated by this finite set, and so will be finitely generated. And to see that, if this set U generates a proper ideal in I, then there's a polynomial, g of x in I, of smallest degree that is not in this ideal. Well, maybe you can see what's coming. There is, because of this special property of U, there is a polynomial of this form, so it belongs to this ideal, whose degree agrees with the degree of g, and whose leading coefficient agrees with the leading coefficient of g. So when we subtract g minus f, we get an ideal, we get a polynomial in I, but its degree is less than that of g, so it must therefore be in the ideal generated by U, but f is in this ideal, therefore so is g. That's a contradiction. So I is finitely generated.